Adrian is with a very strong technical background, but also heavily involved in AI ethics work. So I think Adrian is very unique from a technical point of view, contributing not only to, but the part that I like the most is fairness for machine learning and AI, how these ethical principles can technically grounded into reality. I think that's some kind of lessons that for those AI engineers that can learn from outside China. And then we should, well, people are talking whether AI ethics and AI safety should be another area for AI, but our idea is that it's not another sub area for AI. It's something all the AI practitioners have to keep in mind. So I think Adrian is a model along this line. Thank you, Adrian. The rest is yours.
Thank you so much, Yi, for that kind introduction. It's a great honor to be speaking to you. Thank you so much for inviting us and hosting us so well. Let me check that I can share screen. And sorry if you see some of my notes for a second. Can you see the slides okay?
Yes, we can. Thank you, Adrian.
Okay, fantastic. So again, thank you so much for inviting me. And I really enjoyed Effie's talk. I thought that was great and teased this up quite nicely. I'm going to present joint work with great colleagues, as shown at the bottom of the screen here. And I particularly like to thank the people that are shown in blue here who helped contribute some of the slides. Something is a little weird. Okay. I'm going to, as Yi said, I'm going to present a selection of recent work on fairness in machine learning. The context will likely be familiar to many of you. We're seeing increasing deployment of algorithms in many important settings, which directly affect human lives. There's hope that this might lead to greater accuracy, efficiency, and consistency. But a big concern, of course, is to be sure that people will be treated fairly.
Adrian, sorry, Adrian, to interrupt you. It seems a little bit weird for your slide because we can see your script. Would you like to do it?
Okay. Well, that will make it easier for you to see what I'm trying to say. But hold on one second.
And share it again. But just to bring people's attention to Adrian's background, which I like the most, it seems that Adrian is in China for the airport, at the airport, that he cannot really catch up with the conference, but actually it's just a picture which Adrian liked. And I've seen him using this, and thank you for showing the friendly hand to the audience.
It's my pleasure. I hope I can be there in person someday, and I understand the sentiments that are shown there. I hope are shared by all of us. Does it look okay now?
This is very nice for now. Thank you.
Okay, so you just see the loan application now.
Yes.
Sorry about the trouble before. So situations where we may care about being fair, of course, are many, but a natural example is when deciding whether or not to make a bank loan, or when screening candidates to hire, and perhaps even more importantly in criminal justice, and maybe even especially right now with the ongoing Black Lives Matter movement. We really need to make sure that the machine learning systems which we develop and deploy should treat all people fairly. So this has led to rapidly growing interest in fairness in machine learning. And for those of us in the technical community, it's still early days. We're trying to figure out what we really need in order to make progress on fairness. We like to have precise definitions, but what does fairness really mean? So of course, this has been debated for thousands of years by philosophers, politicians, and by almost all of us. And one common answer to what fairness means is that it means equality of something. But what equality of exactly what? And that was the title of a famous essay by Amartya Sen, who is a Nobel Prize winning economist. So most work in machine learning fairness has embraced notions of group fairness, where we enforce equality or parity of something across different groups as determined by sensitive features. And I've shown here a whole range of different legally recognized protected classes under US law. Still, those maybe will define the classes, but what is the something which we want to hold equal? So there are two main existing notions of fairness in machine learning, both inspired by anti-discrimination legislation. One is parity in treatment, where the focus is on the treatment or the process. And the second is parity in impact, which is outcome oriented, where there the idea is that each group, for example, maybe men and women, should receive a similar fraction of something. And that fraction could, for example, be the beneficial outcome. If a bank is deciding whether or not a customer will repay a loan, then the beneficial outcome will be predicting that the loan will be repaid. Now, this idea that each group should statistically receive a similar fraction of benefits is just one of a range of group statistical approaches which are typically taken. What I've just described is sometimes called demographic parity. And demographic parity doesn't take account of, in this example, creditworthiness. So people have developed many different measures. People are probably familiar, there are over 20 different measures that have been developed that might be alternative definitions. For example, equality of opportunity focuses just on those who will repay, and it says that from that group, men and women should get the same acceptance rates. So sometimes you might call that equal true positive rates, or equal accuracy is another criterion. A whole range of different measures like this. In this talk, to keep things easier to follow, I'm going to focus on parity I'm going to focus on demographic parity as being easy to follow. And when we enforce this measure, we typically allow a small tolerance, but we're going to explore whether, in fact, aiming for parity or equality is too restrictive. Can we do better than that in a principled way? And I'd like you to think about this example. So this was a headline last year. Black people are charged at a higher rate than whites. What if prosecutors didn't know their race? So this illustrates the idea of treatment parity. Indeed, perhaps it would be a good idea if prosecutors couldn't even see the sensitive attributes. That can sound good, but one problem that may immediately come to mind is that we might be able to infer the sensitive attribute from other features. But I want to point out a different problem. So in some areas, unfortunately, historically, blacks were charged by police more than whites were, even if they acted in the same way. And one of the applications that we're going to be looking at very soon is trying to predict the chance that someone will commit a crime in their future. Their prior arrests and convictions can be very important features in making the prediction. So if overall blacks tend to be charged in the past more often than whites, then if we try to predict future crime, we're likely to overpredict blacks' future crime. In order to adjust for that past bias, it would make sense to use a different prediction function for blacks compared to whites. That might seem more fair to do it. However, there's been a lot of resistance to this idea of using different prediction functions for different groups. It can look like we're lowering the bar or using affirmative action or reverse discrimination. So what I'm going to do here is to try to make a principled case for using different prediction functions for different groups based on ideas from economics. The idea is that we're going to move beyond parity, beyond equality, beyond strict equality, and instead explore preference-based notions of fairness. So we're going to be inspired by notions of envy-free fair division. Gamow and Stern introduced these ideas related to cake cutting that some of you may be familiar with from the 50s. The idea is that each participant will be happier with their allocation than if they switched. So no party feels any envy for the other's allocation. We're also going to use some ideas from fair resource allocation in economics, which go back to Foley in the 60s. And the essential notion is we're looking at group envy-freeness, which gives us a justified way to use different classifiers for different groups, provided that each group prefers their own respective outcomes. We'll see that that can lead to significant gains in overall accuracy. Parity in treatment, this is the base notion, requires that we cannot use the sensitive feature. So we have to use just one classifier, and that may seem restrictive. So let me show you an example. Here we have a very simple case. We are showing two features along the x-axis and the y-axis. Men are shown with an M in purple, and women have a W in blue. The green regions are showing true positives, and the red area shows true negatives. So notice that the feature distributions are quite different for men and women. The x-axis is very predictive for women, and the y-axis is very predictive for men. We'll assume that the points are uniformly distributed within each square. And here, for simplicity, we're going to consider the class of linear classifier boundaries. So if we insisted on parity treatment, that means that everybody gets the same classifier, same one classifier, where we aim for maximum overall accuracy. And you can see that that classifier is shown here as a line, and this has accuracy of 83%. It gets all of the women correct. So that's pretty good. But actually, this classifier gets gives all men the negative class. It misclassifies 100 of the men, and that doesn't seem terribly fair. So can we do a bit better than that? So we're going to introduce this idea of preferred treatment, this group envy-free notion of preferred treatment, where we're going to be able to use two classifiers. And the essential idea is each group will optimize its own classifier for accuracy, and we require that no group would prefer to pose as the other group to get the other group's classifier. So let's see what happens here. So we have the old solution on the left, and now the new solution on the right has two classifiers, and we can see it has much higher accuracy. In fact, it went from 83% to 100%. As well as having higher accuracy, notice that men don't want the boundary for women, and vice versa. So just to make that a bit clearer, the men with the men's classifier allow 1/3 of them to get the benefit, whereas if they switch to the women's classifier, none of them would get benefits. The women with the women's classifier allows 2/3 of them to get benefits, whereas if they switch to the men's classifier, none of them would get benefits. So the men don't want the women's boundary, and the other way around. We get significantly higher accuracy, and I hope that this sounds sensible, while hopefully avoiding worries about affirmative action or reverse discrimination. Just summarizing, preferred treatment is a relaxation of parity treatment. In both cases, we optimize for accuracy, but we're allowing a larger set of possible solutions, which lets us improve accuracy. Okay, so now let's go from treatment to impact. If we want a single linear classifier to have parity of impact, that is, if we want to have one classifier that requires both groups get the same benefit, then we get the solution shown here. We have to lose some accuracy compared to the earlier single classifier solution without the constraint. So we get accuracy of 72% with the same benefits for men and women. And now I'll introduce the idea of preferred impact on the right here. The idea here is inspired by the idea of a bargaining solution. Again, we're now going to optimize for accuracy with two classifiers, and preferred impact will enable more benefits to all groups. The requirement is that each has to get at least as much benefit as they did under parity impact. So here we have the preferred impact solution on the right. Both groups are better than they were with the previous parity impact classifier. And in fact, in this case, the preferred impact classifiers are equal to the preferred treatment classifiers that we saw before, but they won't always be. So again, preferred impact is, I hope, a justified relaxation of parity impact, allowing greater accuracy and benefits. With some mathematical details, if anyone's interested, we can get into, or you can look at the paper. Let me just give a quick example on a particular data set. Some of you may be familiar with this. There is a proprietary recidivism prediction tool. Recidivism prediction is predicting whether or not someone will commit a crime. It's important for whether people receive bail, or important for their sentencing in prison. And ProPublica gathered data about this proprietary tool, including a bunch of features like number of prior criminal offenses, arrest charge description, juvenile misdemeanor, etc., along with the actual compass prediction of what happened. And so we have this data set shown here of blacks and whites, and the positive class means that they were predicted not to commit a crime. The negative class means that they were predicted to commit a crime. So let's look what happens when we apply this method. And sorry, there's quite a lot on this chart. Let me try to talk you through what we're showing here. Class 0, shown in red, are blacks. Class 1, shown in blue, is whites. And we have the different cases shown on the bottom here. We always optimize for accuracy, which in each case is shown in gray on the scale on the right, subject to various constraint options. So first, on the left, the unconstrained case, we have two classifiers where each is optimizing for accuracy on each group. We see we get high accuracy shown in gray, but we don't satisfy preferred treatment or preferred impact. We can check that because the benefits are shown by colors on the left. We see a solid bar if a class is using its own classifier, and a hatched bar shows what happens if it were to switch to the other classifier. So in the unconstrained case, you can see that the red hatched bar is significantly higher than the red solid bar, so it's not preferred treatment. Next, if we go to parity of treatment and impact, we have one classifier trained to maximize overall accuracy with approximately equal benefits across the groups with just a little tolerance. And notice we get a large drop in accuracy. The gray bar has dropped very significantly. Next, with preferred treatment, here we have two classifiers. Each group is getting more benefit with its classifier than with the other. That is, the solid bar is at least as high as the hatchet with a little tolerance. And we achieve accuracy now almost as high as in the unconstrained case. So big benefit for accuracy. In the preferred impact case, compared to the parity case, we achieve benefits at least as high with significant accuracy gain. And on the right, if we can have preferred of both, preferred treatment and preferred impact. And you can see that compared to parity, we get gains in accuracy and benefits. So just to recap, we've introduced two preference-based notions of fairness. We've shown that going from equality to preference can be a principled way to improve performance. But there are still some problems. How should we think about fairness when the groups are very different sizes? And if we do that, how should we weight unfairness for each group? And while we've talked about ideas of group fairness, what about what happens within a group? I know I'm running out of time, so I'm going to go quite quickly just over the main ideas for this next part. But let me just show the problem here. So on this slide, if we split the population into male and female, if you look at the accepted individuals, the ones in the circle, then it would appear fair. Similarly, if you were to split by blue people versus green people. But clearly overall, the picture doesn't look good. Everything okay? Okay. Green males and blue females are getting no benefits. So there are various approaches that people have developed to try to deal with this, but I'm going to try to introduce an idea that allows us to think in a principled way about ideas of group fairness that we've talked about, along with ideas of individual fairness. We want to try to make sure that each individual is treated equally. And the way that we do that is we use inequality indices. And I'm going to claim that inequality indices which satisfy certain properties or axioms are very good to adapt to use for measuring unfairness. So inequality indices can be defined in various ways. Many people might be used to the idea of a Gini coefficient, which is plotted on the bottom. This shows Gini coefficient for incomes in the UK over a certain period. The idea is that the lower the number, the less inequality there is. The higher the number, the more inequality there is. So according to this chart at the bottom, perhaps surprisingly, income inequality in the UK has been coming down slightly with some variation over time. So the Gini index is defined by the equation at the top. And there's also a whole set of generalized entropy indices which can be used for inequality, which I've shown here. Alpha is a parameter that lets you focus on different parts of the distribution. So certain things that I claim are desirable in measuring inequality and also for measuring unfairness are these different properties shown here. Zero normalization, so zero inequality if everyone has the same income. Anonymity means we don't look at actual individual identities. scale a population invariant, so if we were to scale up or down all the incomes, it wouldn't change the measure. Or if we were to reproduce the population, duplicate the population, also wouldn't change the measure. And the transfer principle says that if we go from a high to a low earning person, that would decrease inequality. The Gini index satisfies all of these properties, but it doesn't satisfy this last property of being subgroup decomposable. Subgroup decomposability will be exactly what we want. In this case, it allows us to break down the total inequality, or in our case, we're going to measure it as unfairness, into the intergroup inequality together with the weighted sum of intragroup. So it allows us to break it down into between group and within group. And the way that we're going to apply these to fairness here is that we're going to, instead of talking about income, we're going to talk about undeserved benefit that someone gets. So they're going to get, we're going to give them a score of 1 with an accurate prediction, 2 with a false positive, so that's a kind of undeserved benefit, and 0 with a false negative. And let me just show you what happens when we apply that to the same data set we were looking at before. If we use a typical method to control the between group unfairness, so if you look at the plot on the left, this is a prior tool where we can adapt the covariance threshold. As we bring it down from 1 to 0, it forces the between group unfairness to come all the way down to 0. But as we do that, look what happens to within group unfairness. You can see that for white, actually, for much of the time, it goes up, which means that overall unfairness moves around in a way which is hard to predict. And so if all we do is focus on between group unfairness, there's potential for actually increasing the total unfairness. So summarizing, we introduced inequality indices as a flexible, principled way of measuring algorithmic unfairness, providing a unified approach to measuring both between and within group unfairness. So let me just give a quick comment on what next. I suggest that it's really important for us that we don't fall into the trap of just looking myopically at the fairness of an algorithmic system. That is, it's the algorithm and the data. We really want to look at the whole decision process. We want to see what happens when you give these tools, for example, to judges. And there's some early work which was reported here showing that actually you can get unpredictable effects. So even if you try to train your algorithm to make the algorithm as fair as possible, it won't necessarily increase the fairness of the whole process, including the human. So we really need to work together to explore these kinds of questions. We need technical expertise, but we have a lot to learn from everyone, including social scientists, lawyers, philosophers, policymakers, and real-world practitioners. We should engage together to try to make a positive impact on society. Thank you. 谢谢.
Thank you so much, Adrian, for the very inspiring talk. I think right in the chat, there is a question saying that AutoML is increasingly important in machine learning. Is AI capable to detect the imbalance of the sample data? And obviously, just by what Adrian says, of course it can. And but more importantly, also like what Adrian says, it's not only about finding the imbalanced data, but really the full process. And as a technical expert, that Adrian emphasized the interaction, the importance of interactions with social scientists, not only for the technical experts who are not really trained by ethics or social science. Thank you for making that such strong argument and lessons that we can learn from your talk. Thank you so much. For those audience on the video streaming, you can still ask questions so that can be answered by Adrian later. Adrian, thank you so much.
Thank you.
Please join us for the discussion on the panel, if you can, on linking AI East and West efforts for AI ethics and sustainable development. Thank you, Adrian.